In this video, I'm going to show you the Wittig reaction, or it looks like Wittig reaction. This is a reaction that helps us make carbon-carbon double bonds. And making carbon-carbon bonds, you would think, is very common and very easy in organic chemistry, but so far we haven't seen that many ways to do it. So the Wittig reaction was really important. In fact, it was so important that George Wittig won the 1979 Nobel Prize in Chemistry. So let me show you one of the best ways to make carbon-carbon double bonds. Let's jump right in. So George Wittig or Wittig, I really don't care how you say it. I really care that you understand what it does. So Wittig took carbonyl compounds that are either aldehydes or it could be a ketone, two carbon groups here. And he found that he knew that oxygen loves phosphorus, loves to make phosphorus bonds, carbon or oxygen phosphorus bonds. So he took a phosphorus compound. And this phosphorus compound had 3 phenols on it. And it was double bonded to another carbon with whatever on it. Then in effect, I break these 2 bonds and I break these 2 bonds, and we make triphenylphosphine oxide, which is a white, powdery, very stable, sand-like compound. And what you make on the other side is this carbon with a hydrogen and an R group, double bonded to this carbon with its R prime groups on it. And you make a carbon-carbon double bond. So all you need is whatever aldehyde and ketone carbonyl compound, you need a triphenylphosphine that's double bonded to whatever you want on the other side where the oxygen is. So in effect, you just cover up the oxygen and the phosphorus and you end up with what the double bond is. So I guess the question is, how do you make these things, these phosphine compounds? So let me show you. Let's take a look at this example. Here I have a ketone, acetone, and I have my triphenylphosphine compound, phosphorus double bonded to this carbon stuff. First, let's take a look at what the product would be from this reaction. Well, we know that the oxygen and the phosphine part get together and make triphenylphosphine oxide. So on the other side, I have a carbon double bonded to a carbon. This left carbon has its 2 methyls on it. And the right carbon has a hydrogen and an ethyl. So let's look at how do I make this phosphorus compound. So the first step is you take triphenylphosphine, which is a white powdery compound. It's cheap as dirt. And I want this phosphorus compound, this phosphorus part, to react with 3 carbon atoms. I need these 3 carbon atoms to get onto it. So the way we do that is you take 3 carbons with a good leaving group, because these electrons can backside attack this carbon and that leaving group could leave. We attack, the leaving group leaves, and that would be triphenylphosphine. This lone pair is now this bond on, I'm going to draw my CH2 this way, CH2 and CH3. Now we're pretty close to this, except I have this carbon only has 1 hydrogen on it, and here I have 2. So I have to pull one of these hydrogen atoms off. And the best way to do that is to use a good strong base like butyl lithium. The negative butyl lithium pulls off the proton. These electrons stay behind. Oh, and since this phosphorus gave away its electron, it has a positive charge. So once I pull off H+, and these electrons stay on that carbon, it makes triphenylphosphine with a positive on the phosphorus, bonded to a carbon with a lone pair, and it's got a negative charge. And I've got my hydrogen and my ethyl group, which is here and here. Now some people like to draw in this form with a positive and negative next to each other. Whenever you have a compound with a positive negative right next to each other, that's called an ylide. But I like to take these electrons and move them into here and make a double bonded compound. I think that's an easier way to think about it. I like it in the double bonded form, so I move those electrons down. So this compound, you can see, is right here. That's how we make it. So triphenylphosphine, backside attacks the carbon group with the leaving group, and you remove one of the hydrogens, and that gets you to the final product. It's better to backside attack a primary carbon or maybe a secondary, but you don't want this very crowded, and then you remove the hydrogen to make my double bonded compound. Here's the mechanism for this reaction. Let's go through it because maybe it will help you remember how this reaction works. For the mechanism, I like to draw it like this. Let's just pick our ketone. Let's pick one of the phosphine compounds. And let's just put R's on here. I like to draw it this way where the phosphorus and oxygen are next to each other because I know the phosphorus loves oxygen bonds. And because I love to make phosphorus-oxygen bonds, this bond, you could go either side, but you take one of the pi bonds, move it up to make a phosphorus-oxygen bond, and the other bond comes down to make a carbon-carbon bond. So I have oxygen to phosphorus to carbon with its carbon groups on it, bonded to this carbon, which has one bond now to phosphorus, and it has two R groups on that carbon. So the first step is to make this square-looking intermediate or transition state. And then it does it again. So I have oxygen double bonded to phosphorus, triphenylphosphine. And down here I have carbon double bonded to carbon. This left carbon has two carbon groups on it, and the one on the right has two R groups on it. And that's the final product. So you build this square. Just remember the phosphorus and oxygen love each other. So you make that bond first, and you'll remember it takes two arrows to make a square. Do those same two arrows again, and you end up at the final product. Hey, I hope that helps. Understanding the Wittig reaction is a great way to make carbon-carbon double bonds. Think about subscribing to the channel so I can continue to help you with your organic chemistry.